Hey everybody, welcome to OverKill Projects. I'm Walt, and today we're going to take a look at using BJT transistors as switches. And make sure you stick around to the end because I'm actually going to do something that I've never seen anybody do in a beginner tutorial like this, probably for good reason, so we'll cover some of that sort of stuff a little bit later on. And now this tutorial is going to be largely practical, so we're going to look almost exclusively at actual circuits and actual data sheets. And so, let's get right to it and take a look at a circuit that explains why I would want to use a transistor as a switch in the first place. So here's a really common scenario. Let's say I have an Arduino or really any other microcontroller, and I wanted to drive a load that consists of 3 blue LEDs. Now, if you know anything about LED circuits, you also know that I need a little bit of resistance in series with those LEDs in order to control the current that runs across them. And now, taking a look at the data sheets for these blue LEDs, we see that they have a forward voltage of between 3.2 and 3.4 volts. Now, what that means is that if I have 3 of them lined up, I need something like 9 or 10 volts before these things are even going to turn on. Now, clearly my Arduino cannot supply that. And I also want to drive these with 60 milliamps of current. And as it turns out, the ATmega 328P that's on board on my Arduino can only supply a maximum of 40 milliamps. And so you can see that my microcontroller cannot supply enough juice in any way, voltage or current, for me to drive these LEDs properly. So the solution is transistors. Now I have a power supply, so I can supply 12 volts and pretty much as many amps as I want, but certainly enough to drive 60 milliamps through these blue LEDs from my power supply. So if we take a look at this circuit where I have the transistor set up as a switch with the Arduino driving the base, we see that this now works flawlessly. I can switch my blue LEDs on and off with no problem. They take these 60 milliamps or so that they need, and everybody is very happy. Everything runs cool and safely. Okay, fine. So a transistor as a switch works, but how does it work? Okay, now this is where we're not going to really get into a lot of the physics, but the idea is pretty straightforward. Okay, so a bipolar junction transistor, or a BJT, which makes BJT transistor a redundant term, but you're going to hear me say it an awful lot here, so get used to it. But BJTs are made up of 2 different kinds of silicon, hence bipolar. There is an N type and a P type, and the truth is that even those 2 types come in different flavors, which is like why a collector and an emitter are 2 different things. We'll get to that in 1 second. But roughly speaking, a BJT sandwiches 3 layers of those 2 types of silicon, so you can either have an NPN or a PNP transistor. And in either case, each of those layers corresponds to a pin on the transistor, so you have 3 pins, a collector, a base, and an emitter. And now the way a BJT works, once we meet a few different voltage and current criteria, and they're pretty simple, we'll go over them, the BJT takes whatever current we supply to the base and makes a multiple of that current available at the collector. And now the number by which we multiply the base current is usually referred to when you're just talking as the beta of the transistor, but you'll almost always see it listed as HFE in the data sheets. And this HFE value can be as low as 3 or 5 in certain power transistors, but it can be as high as the thousands. But it all depends on which transistor you're working with. And now for this tutorial, we're going to work almost exclusively with the 2N3904 NPN transistor. It's super common, super cheap if you buy it in bulk, and also its PNP brother, the 2N3906. And before we get too far, this is a great spot for me to say, if you like this video, let me know down below by hitting the like button. While you're down there, subscribe, comment, check the description for links to all the stuff we're talking about today. Now, jumping right into the data sheet, if we scroll down a little bit, we're going to see a little section where it lists out the DC current gain. You're going to see that these are listed by collector current. And so the game is this: you should have some idea what kind of current your load needs. We're going to connect that load to the collector, and then we're going to supply to the base an appropriate amount of current so that we have more than enough current available to our load at the collector. And we're going to do that by using this table. You will notice that the HFEs are listed according to their minimum values, and this is for good reason. If you have 2 of the exact same transistor from the exact same company out of this exact same batch, they might have two radically different HFE values. One might have an HFE value of say 40 at your collector current, and another one might have a value of 80 at that same collector current. And so you cannot rely on this HFE value to build some sort of precision circuit, but that's okay. There are ways to design around it. And generally speaking, for switches, we only need that minimum value. And so you might be asking, well, how do I control the amount of current at the base of the transistor? That's something that tends to confuse beginners, but the idea is very simple. We use Ohm's law and a resistor. So we know the amount of voltage that we can apply at the base. So using Ohm's law, we can put a resistor in series between our voltage source, in this case the Arduino, and the base to guarantee the amount of current that we need. And that's what I did in the circuit before with the blue LEDs. You saw that I had a series resistance between the Arduino and the base that was supplying the current that would be multiplied at the collector. Now going back just a little bit, I mentioned that there are a few voltage and current criteria that you have to meet in order for the transistor to function the way that you want it to. Now the first of these, and the one that I think tends to confuse people the most, is the VBE saturation voltage. Now for BJT transistors, when we talk about voltages, we're almost always measuring from the emitter. And in the case of NPN transistors, that emitter is always going to be lower than the base and collector voltages. And in fact, it has to be. If you take a look at the data sheet, if we were to pull the base more than 6 volts lower than the emitter voltage, then there's a good chance we're going to break this transistor. Likewise, you can't have a collector voltage that's too high compared to the emitter voltage, or that might break the transistor. You see here for the 2N3904 that's about 40 volts. So okay, for this NPN transistor, we need the base to be at a higher voltage than the emitter, but it turns out that there's actually a minimum voltage higher that the base has to be than the emitter in order for this thing to function at all. And that's called the VBE saturation voltage. It's usually about a diode drop. And you see here for the 2N3904 that the minimum such voltage is 0.65 volts. So what that's telling us is that the voltage at the base has to be at least 0.65 volts before this thing even has a chance of turning on and functioning the way that we want it to. Now, in the case of a switch, that's usually not a problem. Your microcontroller is supplying 5 volts or maybe 3.3 volts or even 1.8 volts, but at any rate, it's enough to be above that threshold. But that does come in our calculations. Like I said before, what we're going to do is have a voltage supplied by our Arduino, in this case 5 volts. But remember now that we have to subtract from that 5 volts the base emitter diode drop. So now instead of 5 volts across our resistor, we're actually looking at 5 minus 0.65 or 0.7. So it's more like 4.3 volts. The other voltage consideration to keep in mind is that when this transistor turns on, the collector voltage is going to try to drop all the way down to the emitter voltage. So in our case, all the way down to ground, but it's not quite going to get there. And so you'll see in the datasheet that there's this collector emitter saturation voltage given, and that tells you that even when we drive this transistor really hard as a switch, the collector voltage is still going to be about 0.2 volts above the emitter voltage. Again, this isn't usually a problem when you're using a BJT as a switch, but you do want to be aware of it because if you're dealing with a load that has a big forward voltage like LEDs or something like that, or very low collector voltages, you actually might run into problems with this little 0.2 volt drop. And now the third criteria that you have to meet in order for this transistor to work as planned is you have to meet the minimum cutoff current at the base. And so you see for the 2N3904 that the base cutoff current is actually something like 50 nanoamps. So you shouldn't have too much problem meeting that, but I actually set up a circuit to test this. So if we take a look at that circuit, you see that I have a 2N3904. I have about 105 mega ohms between the base and the Arduino. So if you do the math on that real quick, this is going to be below 50 nanoamps. It's actually going to be something like 41 nanoamps at the base. And then at the collector, I actually have hooked up a 1 mega ohm resistor. I have that hooked up because according to Ohm's law, whatever current is available at the collector is going to be multiplied by 1 1 million across this resistor. So if I measure this value, all I have to do is divide by a million, which is the same as saying if I take a look at the voltage across the resistor, that's the same as the number of microamps available at the collector. Okay, so actually powering this thing, we see that we get something like, 138 nanoamps output for 41 nanoamps input, which means that our beta, or our current gain, is way down around 3, which is well below the minimum listed HFE of about 30. But now if I change the series resistance into the base down to 60 mega ohms, then I'm driving the base with something like 70 some nanoamps, and we see that I get a much higher current at about 2.8 microamps, which actually gives us a gain of somewhere between 35 and 40, which is pretty great. That's very much in line with what the datasheet tells us we should be getting once we get up to collector currents of about, 0.1 milliamps. Whew. Okay, so that pretty much does it for what we're going to cover datasheet wise. Now let's actually design a circuit with an NPN and a load. So in this case, again, I'm going to power an LED. I just have a simple green LED that has a forward drop of something like 1.3 volts. I'm going to use a series resistance of 1000 ohms, and my positive rail is going to be at about 9 volts. Now, if I want to drive this LED with a current of about 5 milliamps, then what I need is a current of about 5 milliamps divided by 40 at the base. So 5 divided by 40 is about 1/8, which is 0.125. So I need 125 microamps at the base. I'm actually going to drive it much higher than that. I'm going to use a 10k ohm resistor in series between the base and the Arduino, and even with our forward voltage drop between the base and the emitter, it's going to leave me with plenty of drive, something like 430 microamps at the base. And sure enough, here you can see it switching on and off. It works perfectly. And if we jump over and take a look at the oscilloscope, we actually see what's happening here. The top signal is the base, the bottom signal is the output voltage. You can see at the top that we're simply switching the base on and off up to 5 volts, and the collector voltage at the bottom drops almost all the way down to 0 every time the base is driven high. And we can actually see all the things that we talked about here. Like I said, this LED actually has a forward voltage of about 1.3 volts, and you can see that the collector voltage only gets up to about 7.7 volts or so. And on the flip side, if we take a look at the very bottom of the collector voltage, we see that it never actually gets all the way down to 0. It always hovers just a little bit above. That is the 0.2 or so volts of collector emitter saturation voltage I talked about before. You can see it all in action there, and it all works out exactly as we planned. So now very quickly, let's jump over to PNP transistors and take a look at why they're great. So now for a PNP transistor, okay, all the voltages are still taken relative to the emitter, but now they all have to be lower than the emitter. So the base has to be at least 1 diode drop lower than the emitter, and the collector has to be positioned lower than the emitter as well. And so this might seem confusing because now we're like subtracting voltages instead of adding them, and actually, we have to bring the base low in order to turn the transistor on. But what we gain by that is that our load, which is still going to be connected to the collector of the transistor, is actually also connected to ground. And now there are some types of load that absolutely must have their ground pin connected to actual ground. And so in those cases, a PNP transistor is really your only solution. But you might already see a problem here. If I have my emitter tied to a 9-volt rail and I have my collector tied to what I'm calling ground, well, my Arduino at most can supply 5 volts, which is well below 9 volts. That's a 4-volt difference. Even with the base emitter drop, that means that the base is sitting something like 3.3 volts lower than my emitter, which means that this transistor will always be on. And here is where I'm going to break with tradition and do something that I don't often see done. I'm actually going to hook up my Arduino's plus 5-volt rail to my plus 9-volt rail from my power supply. As long as you don't have the ground pins for both supplies connected together, This is perfectly legit. There's no problem doing this. Well, there is some problem, and that is that USB devices are often connected to actual earth ground, like, ground. Now that's not a problem when using my power supply because that has a floating ground, so that can sort of go anywhere. However, if I go to probe this thing with my oscilloscope, I'm gonna get a big issue because the ground pins for my oscilloscope, the little clamps that come, with the probes, those are connected to earth ground as well. So I have to make sure that if I want to probe this thing, I still have to connect them to the ground pins on my Arduino. Otherwise, I might do some real damage. So you can see that this can get confusing pretty quickly. This is why people don't often do this. But let's just design the same thing that we did before. And in fact, it's the exact same design that we had before. We have the green LED, the 1 kilo ohm series resistor. With that, we have a 10 kilo ohm series resistor between the base and the Arduino. And now when the Arduino goes low, the light comes on. Everything works just like we want. You can see it again here on the oscilloscope. Everything is as expected. However, of course, I don't recommend doing this with all that ground plane nonsense because it gets very confusing very quickly. There is, however, a perfect solution, and it is this circuit right here. Now, I am not going to tell you how that circuit works because we have gone over everything that you would need to figure out why this is the ideal solution to our problem. And since I have found that experience is absolutely the best teacher, I recommend that you go out, build yourself a whole bunch of different transistor switch circuits, including that last one that I showed you. Make sure that you understand how they work. It's worth, 1,000 words. We could sit here and hash out the math all day, but until you build a bunch of these circuits, you're not going to get a really good feel for how that math should shake out. Okay, so we just covered a ton of material. I'm going to cut it there for today. The next time I do a tutorial, I think we're going to do something like voltage followers, and then after that, we're going to do amplifiers and probably FETs and all that sort of good stuff, but I'm only going to do it if you really like it. So if you like today's video, let me know down below. Hit the thumbs up, the like button. Make sure you subscribe while you're down there. Comment down below to let me know what you liked, what you didn't like about this tutorial, and check the description for links to everything that we talked about today. And I will see you next time.